Hello, and welcome to a lecture on optics of axisymmetric paraboloidal reflectors. My name is Steve Ellingson. Here's an overview of this lecture. The idea is that defining geometrical relationships that are needed for the analysis and design of axisymmetric paraboloidal reflectors are going to be established in this lecture. So I should define two terms right up front. First, paraboloid. A paraboloid is a body of revolution based on the parabola. So I think we all know that a parabola is a function that looks like this. And to obtain a body of revolution, you simply rotate this shape around the axis, right? So we could call this the axis. Maybe this is the z coordinate. And then we rotate the parabola around this axis. And we get a shape that looks like a bowl. And that bowl then is our paraboloid. By axisymmetric, we mean that the outline of the reflector edge is symmetric around the axis of rotational symmetry. So as I've drawn here, this is axisymmetric. This is in contrast to an offset-fed reflector, which, for example, might look like this. Here's the z-axis. Here is a paraboloid, which is axisymmetric, but I might just take a section of the paraboloid up here. Now that is certainly a paraboloidal reflector, but we call this offset as opposed to axisymmetric because the shape of the reflector is not symmetric around the axis of rotational symmetry. Most common circular reflectors are axisymmetric in this sense. So the topics we'll cover here are spherical to plane wave conversion. This metric, which is commonly used to describe all kinds of reflectors that are based on paraboloids, that is f over d. And then angle to rim, which we'll call theta naught in this and future lectures. So f over d and theta naught are the two parameters that are commonly used to describe axisymmetric paraboloidal reflectors. Okay, spherical to planar conversion. Now, we're referring to wavefronts. So the idea is that if we have some feed, and that feed radiates spherical wavefronts, what we'd like after reflection is a plane wave. Now, it's no secret that the shape that does this is a paraboloid, but for the moment, we'll just leave the shape generic, and we'll see that this requires a paraboloid. So to define the geometry here, we need a coordinate system. The origin is located here. The z-axis goes this way in the direction that we would like the transmitted wave to go. Then it's convenient to define a second coordinate system, the sub-f coordinate system. So in the sub-f coordinate system, it points this way in the direction opposite z. In other words, towards what we refer to as the vertex of the reflector. F stands for feed. So now we have two coordinate systems. We have x, y, and z, sometimes referred to as the global coordinate system, and then the feed coordinate system, x, f, y sub f, z sub f. And I've shown you how z and zf are related. Now, in this system, we'll define a distance f, which will turn out to be the focal length, but for now we'll just call it f, and it's the distance between the feed, or the origin of the coordinate system, and the vertex of the reflector. Now from ray optics, we know that, at least if we're in the ray optical regime in terms of frequencies, that we can describe the scattering in terms of reflection. So for any given point of reflection q, we can determine a direction of reflection, which is going to be this way, and it's going to be related to the surface normal. So n hat is the normal to the surface. Now we desire the length from this point O, the origin, to point Q, that's OQ, and then from point Q to point P, which is out here, to be a constant. If we have that, then we know that we'll have constant phase along this plane, and that'll result in a plane waves then, as it's reflected from the surface. So we can see that this requires that this length be 2f plus z. For example, the distance from here to here is f, back is f, and then to here is z. So as I've drawn here, that path is f plus z, or 2f plus z. So if I want constant phase, every other possible path, such as this one, should also be 2f plus z. So I can write this out in a little bit more detail. This distance here from the origin to the point of reflection we'll call r sub f. So that distance from the origin to the point of reflection, r sub f, plus z sub f plus z, then must equal 2f plus z. So this distance and then this distance must equal 2f plus z in order to have a plane wave in reflection. So this gives us the relationship r sub f plus z sub f equals 2f. And once again, we have not yet established that f is the focal length or even that this is a paraboloid. We're simply determining the requirements to achieve this effect. So what shape does this? Well, we've just established that this is what we want. If we square both sides of that equation, we get on the left rf squared times 2 times r sub f times z sub f plus z sub f squared. And on the right, we get 4f squared. We know from the geometry of the problem here, and this is a very simple Pythagorean relationship, r sub f squared must be x sub f squared, y sub f squared, z sub f squared. And furthermore, this here is the radial dimension, which we've been calling rho, so we might as well call it rho sub f squared, and then here's z sub f squared. So we can rewrite r sub f squared as rho sub f squared plus z sub f squared. That gives us on the left rho sub f squared, 2 r sub f z sub f, plus z sub f squared. Now we can reorganize factors. So on the left, we have just r sub f squared. On the right, we have 4f squared minus 2z sub f, which we've pulled out, and then the quantity r sub f plus z sub f. And we've already established that this quantity in parentheses should be 2 sub f, so we can make that substitution. So now we have rho sub f squared equals 4 sub f times f minus z sub f. Solving for z sub f, we have that z sub f should equal minus 1 over 4f times rho sub f squared plus f. Now again, I'll point out that we didn't assume any particular shape here. We've just figured out what requirements there are on the surface. However, we have established that this is a defining relationship. This is required property of the surface. And you can see right away that this is a parabola of revolution, or a paraboloid. And the way to look at this is in the feed coordinate system. So here's rho sub f. Remember, that's square root x sub f squared plus y sub f squared. So that's the radial dimension from the axis of symmetry. This is pointing back towards the vertex. So that is going to be the vertex. And if we plot this equation, z sub f as a function of rho sub f, it is immediately clear that this is a quadratic equation. Therefore, we end up with a parabola. This dimension here, from the origin to the vertex, is f. That's where we started. So f is now clearly focal length in the traditional optical sense. And it's also worth noting that this dimension from the origin out to the point on the paraboloid, which is in the same plane as the origin, has a distance 2f. That's sometimes useful to know when we're working the geometry of these problems. So once again, the distance from the origin to the point on the paraboloid that's in the same plane is 2f. Okay, now f over d. The idea is this: an axisymmetric paraboloidal reflector is completely defined by the parameters f and d. In other words, by the focal length, which we've already established, and d. d is the new thing. D we'll define as being the overall dimension of the reflector. All right, so in a circular axisymmetric paraboloidal reflector, D is the diameter, which is why we use the letter D. Now, this sometimes gets confusing because we also like to use D as directivity. That's clearly not what I'm talking about here. Here, D is diameter. Now, F over D for typical reflectors is usually between 1/4 and 1/2, but sometimes up to 1 or larger, but typically between 1/4 and 1/2. Here's a picture which kind of illustrates the range of possibilities. So here is the focal point, which we've been calling O, and this is the vertex for the F over D equals 1/2 reflector. And then what we're showing here is the different shapes that you get for different F over D ratios. So in other words, if you take D as an independent parameter and then you calculate the shape of the reflector for a given F over D, these are the shapes you get. So, for example, for F over D equals 1/4, well, that's this shape right here. We say that an F over D reflector has high curvature, and sometimes this is referred to as a deep reflector. The rim lies in the focal plane for an F over D equals 1/4 reflector. In other words, if we go out in the focal plane, that is the plane that contains the focal point, we find that the edges of the reflector lie in the focal plane. So this is another reason why this is an important F over D ratio to know about. It has that particular property that the rim lies in the focal plane. We say that such reflectors are typically under-illuminated. What do we mean by that? Well, typical feeds have patterns which are kind of like cosine theta, or in this case, cosine theta F. And in that case, then, most of the energy from the feed will land in a relatively small part of the reflector, and out here we'll get relatively little energy from the feed. So in that sense, we say it's under-illuminated. And this will obviously have consequences in terms of the performance of the reflector antenna. We'll certainly come back to that in a later lecture. The other extreme in this range is F over D equals 1/2. And that's what we have here. So an F over D equals 1/2 reflector we say is relatively flat. In other words, it has low curvature and relatively shallow. So when people refer to a shallow reflector, they mean the F over D ratio is relatively large. Such dishes are typically over-illuminated. The same feed, now projected into the new shape, we see at least illuminates the whole reflector and probably has some spillover, which is significant beyond the edges. So in that sense, we say it's over-illuminated. The feed well illuminates the reflector and furthermore spills over a significant amount of power beyond the edges. It's worth knowing that over-illuminate is effectively a waste of power. Right? If you're transmitting power from the focal point and a lot of it's spilling out beyond the reflector, it's being wasted. So typically this is not of interest to have very high F over D ratios, but every once in a while it becomes important or unavoidable. Paraboloidal surface geometry, distance from focus to the dish surface. Let's investigate that a little bit more carefully. This is one of the relationships that we came up with. We can replace Z sub f with this expression R sub f cosine theta sub f. That's simple geometry. Then we can solve for R sub f. When we solve for R sub f, we get this expression 2 sub f over 1 plus cosine theta sub f. We can use the trigonometric relationship cosine squared equals 1/2 1 plus cosine 2 times the original argument to replace the bottom, the denominator. And this gives us the expression f secant squared theta sub f divided by 2. So what we have found is that the distance from the focus to the dish surface is given by the focal length and the angle to the dish surface that we are considering. The last parameter I'd like to consider here is angle to rim, theta naught. Now, we know that rho sub f, this radial distance is r sub f sine theta sub f. That's straightforward geometry. And now we can expand this. The idea is that we already know that r sub f is f secant squared of half the angle to the point on the reflector. So that's this expression. Sine theta sub f, that's a trig relationship or trig identity. 2 sine theta sub f divided by 2 cosine theta sub f divided by 2. Again, a trig identity. And we multiply those two things together, and we find out that rho sub f is 2f times tangent theta sub f divided by 2. So now we can calculate f over d in these terms. F over d is just f, and then in the denominator, d can be written as twice this radial distance when theta sub f equals the angle to the rim. Now we can substitute the expression that we came up with in the line above into the denominator, and tangent can become cotangent once we take the reciprocal, and we end up with f over d equals 1/4 times cotangent angle to the rim divided by 2. So let me show you how this plays out. We have a relationship now between f over d and angle to rim. So here's angle to rim in degrees. Here's f over d. What we find, for example, is that for f over d equals 1/4, that angle's 90 degrees, as I promised you it would be earlier. As we get to f over d equals 1/3, that angle becomes 73.7 degrees. As we get to 1/2, it becomes 53.1 degrees. And we see, in fact, that this is becoming over-illuminated. All right, this is well illuminated, possibly under-illuminated, and then going to over-illuminated because we are subtending smaller and smaller angles with increasing f over d ratio. That concludes this lecture on optics of axisymmetric paraboloidal reflectors.